Hello, welcome back, everybody. So it's my pleasure to introduce our next speaker, Lucia Cordova, who's going to tell us about non-invertible symmetries and scattering amplitudes.
Yeah, so thanks a lot for the invitation to speak here. And I will be telling you about this work done in collaboration with Christian Kopetti, who's around, and Shota Komatsu. We put out this paper, I don't see that. There's no pointer.
There was a pointer, like 1 second ago. No, there isn't. Just a bit.
Okay. Yeah, earlier this year, and something that is to appear. And the idea is to explore the interplay between these non-invertible symmetries you're all familiar with and scattering amplitudes. So, some motivation. Here at this conference, we all agree that symmetries and their anomalies are very important concepts in physics. They give us constraints on the dynamics of QFTs. And these concepts have been refined and generalized in the last years. So we have these generalized symmetries. No? And what we're trying to answer here is what are the implications of these generalized symmetries for scattering amplitudes. And the punchline of the talk will be the following, which is that crossing symmetry of the S matrix gets modified in the presence of some non-invariable symmetries. So we expect this to be true in a more general setting, but the explicit checks we did were in 1+1 dimension for interable RG flows. So as an appetizer of what's to come, let me study a particular RG flow, which is interable. And this is a flow from the tricritical Ising model to a gapped phase with 3 vacua. So if you deform the tricritical Ising model by this 513 operator or subleading energy, depending on the sign of the deformation, you either go to the critical Ising, so the previous minimal model, or to a gapped phase with 3 vacua. So we will be studying RG flows of this type in the left. And the objects we study are the two-body scattering of the kinks that were mentioned in the previous talk that interpolate between the different vacua. So we have these A, B, C, D labels for the vacua, and then these lines are the kink world lines. So this amplitude should satisfy various properties, among which we expect this crossing symmetry, which is a symmetry in which we exchange in and out particles, and it gives you a relation between S and T channel processes. So in terms of this rapidity theta related to the Mandelstam invariant S, it's between theta and I pi minus theta. So going back to this flow here, more than 30 years ago, Zamolodchikov bootstrapped the non-perturbative amplitude for this flow and got the following expression using unitarity, crossing, and the fact that you have interability. So in this expression, there are some non-important factors here, some oscillating factor in terms of these coefficients D that will be the quantum dimensions, and then these two terms that get exchanged through this crossing symmetry. So this was 30 years ago, but now we know that along this flow, we preserve some of the non-invariable symmetries of the tricritical Ising. So namely, we have this N line that gives you non-trivial constraints on the amplitude. So we expect this amplitude to commute with the symmetries. And to our surprise, we found that this amplitude in the literature is not compatible with these word identities. So what we did was to bootstrap this non-perturbative amplitude from unitarity, interability, and the fact that you have this non-invariable symmetry and you should satisfy these equations. And you get this expression, which is basically the same except for this oscillating factor. But of course, something has to give, and we get a modified crossing condition, which you can see clearly by exchanging these two terms. So in the rest of the talk, I will try to make this more clear. Yes?
So normally when I'm crossing, I'd expect to have conjugation matrix. Oh, sorry.
Normally, when I wrote crossing, I'd expect a charge conjugation matrix in the crossing relation.
Yes, but I think here you don't have any charge, so...
Was the backward like self-development?
Sorry.
Yeah, there's no chart. There's no chart. There's nothing you can do to this.
Yeah, in other words, these lines don't have any arrows. Okay, so yeah, this was an appetizer. Now we'll go through some details. So this is the outline of the talk. I will review some aspects of fusion categories and some symmetries that we have in the minimal models. This is mainly for notation purposes. Then I will explain more about these kink scattering amplitudes and how we can derive this modified crossing. And then I will tell you about this new work in which we bootstrap the space of general amplitudes, not only interval ones, using these modified crossing rules. And I will end with some final remarks. So for the first part, now we have this understanding that global symmetries in QFT are given in terms of some topological operator, which allows you to generalize our usual group notion to higher form and non-invariable symmetries. So what I will be discussing here are zero-form symmetries in 1+1 dimensions, including non-invariable ones. So we will be dealing with topological lines, and the mathematical framework is this fusion category. And the data that we saw in the previous talk already that we need are the topological lines, the fusion coefficients, which tells us how we can fuse these lines together, the quantum dimension given by the expectation value of a loop of these lines, and the F symbols or tetrahedral symbols that gives you relations between how you can fuse diagrams in different ways. So these are some numbers that will appear in our formulas. And to remind you of which topological lines you have in the minimal models, these are the Berlinde lines, which have the same fusion algebra as the primaries. And they act on operators like this, where you have the modular S matrix. So some examples are the critical Ising, in which you have 3 primaries and 3 lines. One of them is this Kramers-Vanier N line, which is non-invariable, and it has this √2 quantum dimension. So this is a C2 Tambara-Yamagami category. For the tricritical Ising model, you have 6 primaries and 6 lines, 3 of them for, again, this Z2 Tambara-Yamagami. You also have this W line, which forms this Fibonacci. So you have this fusion rule we saw earlier, and then 2 extra ones. And something I want to remind you of here is that these non-invariable symmetries, if you have a QFT with these non-invariable symmetries, they're often incompatible with a trivially gapped phase or anomalous. So whenever you have a quantum dimension that is not an integer, then you should flow to a gapped phase in the IR with degenerate vacua. So we will be dealing with RG flows here, which indeed have this degenerate vacua, because we want to scatter kinks. So some of the symmetries that you preserve with the formations of minimal models can be, well, all of them, sorry. You can get them by simply asking that they commute with the deformation. So you have this equation here. So for instance, for the tricritical Ising model, this Z2 Tambara-Yamagami is preserved along this 513 flow that I mentioned at the beginning. And you have these 3 vacua, and you can see how the symmetries act on the vacua. So the N line maps adjacent vacua, and you have this eta line that maps the left and right. And indeed, you have the correct fusion rule. Some other deformation that will appear is this 5-to-1 deformation, or subleading magnetic, that preserves this Fibonacci category. So this will appear in the bootstrap. And more generally, these 513 deformations of the unitary minimal models give you this picture here, where on one side you go into the previous minimal model, and in the other one you go into a gapped phase with N-1 vacua. And the lines preserved that you can get from this equation here are the ones labeled by R,1, and they form a AN fusion category. So the last thing I want to say about these deformations is that as you can see from Virasoro, you basically have some higher spin charges whenever you deform with these three operators, 1, 3, 2, 1, and 1, 2. So these deformations are integrable, and you can construct the exact non-perturbative S matrix for the QFT describing these flows. Okay, so that was the first part. Now let us go into the scattering amplitudes. So as I said, we will study the two-body scattering of kinks interpolating between different vacua. And they are functions of the rapidity or the center of mass energy related in this way. Then the T Mandelstam invariant is just 4 minus m squared. Sorry, 4 m squared minus s, or theta going to I pi minus theta. And what we want to do is to bootstrap these amplitudes from general axioms. So the first one is unitarity, which tells us that for the full S matrix we have S dagger S equals 1, which gives you this inequality for when you restrict to two particle states as in and out. Then you expect this crossing property, which exchanges, is a symmetry you get by exchanging in and out particles. So in this two-dimensional picture, it's basically seeing time flowing in this direction or in this other one. Then if you're dealing with an integrable theory, you should satisfy these equations known as Jahn-Baxter equations, which tells you that the scattering is factorized, so everything is written in terms of 2 to 2 scattering, and you should get the same if you do it in different orders. And you also have no particle production, so that the 2 to 4, 2 to 6, etc. processes are set to 0, which means that you actually get an equality on this side. So it's in the case of integrable theories. This is why I put a star. And this is what Zamolodchikov used to get the amplitude I wrote earlier. And indeed, you get this expression here with some prefactor that takes care of unitarity, this oscillating function in energy or the rapidity, and these two terms that get exchanged in crossing. So, but nowadays we know that along these flows from minimal models, or in general, we can have more symmetries, in particular non-invariable symmetries, and we expect the amplitude to commute with these symmetries. So that gives us some word identities. And this amplitude does not satisfy this equation here for the non-invariable symmetries. So basically what spoils this equation is this oscillating factor here, which is kind of strange anyway, because it tells you that as you go to larger energies, you have some oscillating function, which is a bit strange. So now if you instead use just unitarity, integrability, and the fact that you have these symmetries, you get this other amplitude, where indeed you don't have this oscillating factor, so that's nice, and you preserve the symmetries. So what we're seeing here is that these 4 conditions are not compatible, and something has to be modified. And since we know that these theories are unitary, integrable, and have these symmetries, then what we need to change is crossing. And you see that the coefficient you pay are the square root of the quantum dimensions. So this is for a particular integrable example, but we have now a more general understanding of why this should be the case. So these new crossing rules can be understood from normalizing properly your in and out states, taking into account that now you have some topological degrees of freedom. So the amplitude is basically the overlap between an in and out state. So you prepare some in state with some boundary conditions DCB, and an out state with conditions DAB. And the overlap is given by this function I was writing before, modulo some kinematic factors and the momentum conserving delta function. But basically, this function here, you can think of it as going into Euclidean signature and thinking of the partition function with these boundary conditions and some boundary changing operators in a very large Euclidean disk. And this is just naively crossing symmetric. So what's happening? And the point here is that in order to have this unitarity equation, we should normalize our states properly. And we can do that using the TQFT data. So what we will use is that the vacua can be identified with the symmetry lines, namely we're in the regular model category, and also that these kinks act as a symmetry line. So for instance, in this flow from tricritical, we can associate to a kink this N line that precisely mapped one vacua to the next one. So using this, we can evaluate these in and out norms using the TQFT. And basically, for the in state in the S channel that I wrote here, you would get a network of lines like this, with V going vertically, which you can evaluate using the category. And similarly, for the out state, you get the same, but now with the label A, since you had A here. So now the properly normalized amplitude will be this one, where you get the square root of these norms. But the crucial point here is that in the T channel, namely when we see time going in this direction, these norms change, basically because we need to put the V lines horizontally, so that if you want to relate S and T channels, you get this equation here, where you need to pay these crossing coefficients that indeed in these examples we used evaluate to these quantum dimensions. So this is the general physics derivation of why we need this modified crossing. It comes from normalizing properly the states using the TQFT. Okay, so now let me go to the new part and try to do S-matrix bootstrap. So the idea now is to try to bootstrap or get bounds on the space of all QFTs that have a given categorical symmetry. So what we will do is to try to bound the two-body kink scattering. So this function again, now I'm writing it in terms of the Mandelstam invariant S, with a given fusion category. So we want to make sure that it satisfies these word identities for a given symmetry. So what you can do is to project into different fusion channels that I'm calling here chi. So these V lines are the lines associated with the kinks, and chi is what appears in its fusion. And these p chi's are the projectors into a given fusion channel that trivialize these word identities. So for instance, in this regular representation, they're given just in terms of the F symbols. And for this AN category that we find in these 513 flows, they evaluate precisely to these Kronecker deltas that appeared in the amplitude. Another thing we know from symmetry that we also heard about in the previous talk is that the kinks are degenerate in mass because they form a symmetry multiplet. And I think we will hear about this later in the conference. So we will also use this mass degeneracy. And then the other things that I mentioned before are unitarity, which tells us that for each of these partial amplitudes A chi, its absolute value is bounded by 1 for physical values of the energy. Then this modified crossing condition I wrote before means for these partial amplitudes, this one here, so it mixes different fusion channels, which happens also for group symmetries. And then something I didn't mention before, but is important, is analyticity, which tells us that these amplitudes A chi are analytic in the complex S plane, except for possible singularities related to bound state poles or cuts for multiparticle thresholds, etc. So we need to fix the spectrum in order to know which type of analytic functions we have. So with these 4 ingredients, now what we want to ask is, given a fusion category, what is the space of allowed amplitudes A chi? So one is to get these bounds numerically most of the time by maximizing some type of functionals. So here we will be exploring the space of these amplitudes at a given energy. And we've done so far 2 examples, so 2 different categories, and I will show the results. So the first example is this AN category that we found in the 513 deformations. So we will use the regular representation so that we have n-1 vacua that are labeled as 0, 1/2, etc. Then we will consider theories with the minimum spectrum required by symmetry. So we have these kinks that interpolate between neighboring vacua with a generate mass m, and we don't put any other stable particles, so we don't have any bound state poles. So this means that we have this type of processes allowed where neighboring vacua differ by 1/2. Then setting V, this kink line, to 1/2 gives 2 fusion channels, so that we have 2 partial amplitudes that we need to bound. And using some numerical tools, we input this analyticity, modified crossing, and unitarity to get bounds on this subsection of the allowed space of amplitudes at a given energy. And what we get is this plot here. So the 2 axes are the 2 amplitudes at a given energy, around 3 m². And what we see is that the regions inside these lines are allowed, they are compatible with all these axioms. So let me recall, these are non-perturbative amplitudes, so in general, they're very hard to find. And outside of these lines, we are ruling out possible theories. So it has this nice shape with 2 vertices, and actually at these lower vertices, we have an iterable solution, which is precisely this 513 deformation of the minimal models we saw earlier, given by these expressions here. And basically there is a Z2, well, you can exchange the upper and lower vertex by putting an overall minus sign. So this amplitude is also iterable, but we don't know the model for it. So we see iterability that we didn't give as an input appearing at special points on these bounds. And also the rest of the amplitudes that you can read off at the boundary here of the allowed region have no oscillation, so they have a good large energy behavior, which is something different from other group symmetries where you do a similar procedure, you get these oscillations. So it's something nice. And now the other example I want to give is this Fibonacci category. So here we have 2 vacua and 2 fusion channels. So again, 2 amplitudes we want to bootstrap. And the minimum spectrum now consists of a kink, an anti-kink, and a breather, which is something that interpolates between the same vacua 1/2. So now you have this type of allowed processes. And because you have this fusion rule in which you have V times V and V on the right-hand side, you can interpret this breather as a bound state of these kinks, which in this S-matrix bootstrap means that you can put a hole at that mass, so they all have the same mass, m², and this will give you the bound state pole, and the residue is a cubic coupling squared. So now we have this extra parameter that we also want to bound. So we perform some numerical bootstrap. Now we're trying to bound these 3 parameters, and we get this 3D shape. So it looks like a cone or a sphere. You have 1 point here, which gives you the amplitude with the maximum cubic coupling allowed. And then some shape that gets larger as you go to zero coupling. So here I'm plotting the projections into this two-dimensional plane of these slices for a given G. So something nice that we found is that for a given coupling here in this light blue, there is one iterable solution, which is precisely the 5-to-1 deformation of the tricritical easing that, as I told you at the beginning, preserves this Fibonacci category. And then you don't find any other interval amplitudes until you go to this G equals 0 slice, which is actually the same region that we found for A5. And this is because, okay, mathematically, it's just the same equations that this AK need to satisfy. But the physics is different because in the other case, we were dealing with theories that would flow to a gapped phase with 4 vacua, whereas here it's 2. So the relation between the two is this Z2 orbifold of A5. So basically, you identify these labels here. So indeed, if you had 1 here at the top, now it becomes 1/2, so you get this allowed scattering. And these vertices are, again, interval solutions. But now, instead of having this 5-1-3 deformation of minimal model, you have the Z2 orbifold version of that. So we get a deformation of 3 state spots by these CZ bar operators. And yeah, so we see there are these 3 interval solutions appearing at vertices. It's not super clear, but this is also a cusp. Again, we don't find any type of oscillating behavior in energy for the boundary S matrices. And the fact that you have this Z2 orbifold picture at G equals 0 gives us an enhanced symmetry, not just Fibonacci, but now we have this Fibonacci times the dual Z2. And this actually can happen only at G squared equals 0, because whenever you have this symmetry, the breather, you cannot interpret it as the bound state of the kinks. So the coupling has to be 0. So this is the second example we show in the paper. And let me go to the final remarks. So to summarize, in the first part, I talked about the results in this paper here, in which we show that non-invariable symmetries lead to a modified crossing condition for the amplitudes. And we checked this in various interval theories. We expect this to be generic for when the IR is described by a non-trivial TQFT. And we also showed that these modified crossing rules come from the corrections to the in and out norms by the TQFT. Now, in this paper to appear, I told you about this S-matrix bootstrap part, in which we find bounds on general QFTs with that given symmetry. And I showed you examples for AN and Fibonacci, where we see that interval models appear at special points. And something I didn't talk about, but is also in this paper, is that we extend these results to the non-regular representation. So now we have to deal with possible model categories. And in our formulas, we will have, instead of quantum dimensions, relative Euler terms, dual boundary of symbols, etc. And also, we have a nice argument using SymTFT, in which we can separate the symmetry part from the dynamics. And for future directions, these are some things that we want to do or are doing. One is to test the interval S matrices that we found using something called thermodynamic Bethe ansatz for twisted sectors. Another direction, obvious direction, is to extend this to higher dimensions. So these are 2 possible targets. Then we can also do bootstrap for other categories. A nice one would be Hagerup, that might give us some hints about the field theory realization for this category. And finally, it would be nice if we can see this as a toy model to understand soft dynamics in gravity and gauge theory. Thank you.
Questions?
I missed one point. When you do this S-matrix bootstrap, are you inputting integrability or not?
No, I think the mic is off. So the question was if I was inputting integrability or not. No, the only thing I'm inputting is this. So the fact that I have some categorical symmetry, unitarity, and modified crossing and analyticity.
Then all the models that you are discovering are all integrables.
No, only the ones at the vertices.
Oh, I see. So,
Yeah, so it was very fast, but yeah.
Okay, but sorry, another question. Then, do you understand that these models are integrable because you recognize the model and you know that it's integrable, or because of the position of the point you can understand directly that's...
No, you need to check Yang-Baxter equations. So these equations with the 3 lines in different orders, which are non-trivial when you have indices. So we check that numerically, and then, okay, you see it matches. In this case, it was very simple. We saw it matches the solution.
Yeah. From the point you understand the altering amplitude, and you check that it's integrable. Okay.
But we also, so something perhaps I didn't emphasize is that with the numerics, you get these bounds. So you're bounding these 2 parameters, but you also get the amplitudes that give you these optimal bounds. So I know the amplitudes all along the boundary, and I can just test Yang-Baxter in each of them.
I think we can have one more question. Is that where you wanting to ask a question?
Jared, you had one. So when you apply to Hagerup, thanks for this really nice talk. When you apply to Hagerup, what is there a problem? Because it's a natural thing to apply to and then see what you get.
There is no problem. We just wanted to do like simple categories first to fix our program. But yeah, I forgot now, but at least in the cases I mentioned here, you always have just 2 fusion channels, so 2 things you need to bound. In Hagerup, I remember which ones there are, but you have many more lines. And so yeah, it's just more parameters to fix. And yes.
But conceptually, there's no difference.
No.
Last question. Yeah, please go ahead.
About example 1. So for the other king, I think one candidate will be the SU2 level n-1. What's familiar with the model is the JJ bar deformation. That preserves the AN category, if I remember correctly. It has this. The corresponding guarantee is correspond to regular module category. Do you know where that?
I thought it was just Z2.
No, that was SU2 level 1.
Sorry, you're saying SU2 level?
SU2 level n-1.
Ah, okay.
So for the particular case, in the SU2 level 2, that's just isomplicity in the short indicator.
I see.
There's a whole power. And if you do the junior bar deformation, it preserves the full AN category, and also the TQFT has the same degenerate boundary.
And it's integrable?
It's integrable R2.
And it's different from this?
I don't know, so I'm asking where does it sit. I'll reach it.
Okay, yeah. So if it is at the boundary, then the only solution is here. But inside, you can have many, many things. So you can construct many other integral amplitudes inside, for instance, by multiplying by CDD factors. But it's a good point. We should look. Thanks.
Okay, we should move on to the next speaker. Let's thank Lucia for a very nice talk.